Good afternoon, everyone. This will be the second and final lecture on gear design. Last time I talked about gear kinematics, really, and how you put them together to make a gear train of some ratio. So now we're going to focus on how to calculate the stresses and determine the life of the gear set. So what you're looking at here is a free body diagram of a pair of teeth, part of a pinion and a gear, showing the forces at the interface where the teeth interact with one another. And the force of most interest is labeled W sub T for tangential, shown here, downward on the pinion and upward on the gear. And that is, as its name implies, tangent to the circle. I'm showing it at the pitch point, which lies on the pitch circle. And the pitch circle, you may recall, is the theoretical cylinder from which the gears are generated. So the teeth live above and below the pitch circle, with the addendum and dedendum, respectively. So TP represents the torque on the pinion. TG would be torque on the gear, which is shown right here. So we have a torque on the pinion, we have an omega of the pinion, and from basic geometry we can say that the tangential component of the force at the gear tooth interface is the torque divided by the radius. So TP over RP. And we could substitute diameter of the pitch circle and stick a 2 in the numerator to make it come out right. And we could also substitute for the pitch diameter of the circle, the diametral pitch divided by the number of teeth. So there's three different flavors of the same equation, depending on whether you want to work in terms of diametral pitch, which is tooth size and number of teeth, or you want to work in terms of actual pitch diameter. It's not very often you want to work in terms of pitch radius, but you could. And we have a pressure angle labeled phi, which we defined before in the previous lecture and also defined in kinematics, same idea for both gears and cams. And that defines the angle along, or the line, I should say, along which the true force lives. The so-called line of action is the term used in gears. We called it the axis of transmission in linkages. We called it the common normal in cams. It has a bunch of names that all mean the same thing. It's a line normal to the tangency between the two things that are pushing on one another, in this case the teeth. And as I explained to you in respect to the involute gear tooth shape, the magic of the involute is that that line always stays at that 20 degrees, and for all positions of any teeth in the mesh, the point of contact will lie on that line, and that's what gives us the constant ratio. So I can calculate that big W from the components WR and WT, and WR is simply WT tan phi, and big W without the subscript is just the Pythagorean theorem on the two components. We don't even need to bother to calculate the W because we're really primarily interested in the two components, WT and WR. WR, radial component, is trying to push the two gears apart. So it shows up back at the pivots as a reaction force, which I've labeled RR. And of course we have the reaction force RT responding to the WT, and those two make a couple which balances the TP. So that's a complete free body diagram of a pair of teeth in mesh. And the note at the bottom says, if your contact ratio is greater than 1, which is desirable. Remember, the contact ratio is essentially the average number of teeth in contact in the mesh at a time as the teeth move in and out of the mesh. So if it were 1, that would say I have one tooth pushing on the other, and when those two part company, another one picks up at that same instant. So I only have one tooth pushing at any given time. which is not as good a deal as having a couple of teeth pushing at the same time and sharing the load. So the AGMA guidelines suggest that we want to have the contact ratio between 1 and 2, and you might wonder why they don't say, well, make it 10, because then you'd have 10 teeth on average pushing, and we'll address that in a slide still to come, because the likelihood of the gears being accurate enough that you would really have 10 teeth pushing all at once is very slim. So to be conservative, they say, well, even if you have theoretically 3 or 4, we'll call it 2. But if it is greater than 1, let's say it's 2, then I will have something called the highest point of single tooth contact, abbreviated by this mouthful, HPSTC, which simply means that the tips of the teeth will never be pushing on one, or the tip of one tooth will never be pushing on the other, because by the time it gets to that point, another tooth is picked up, another pair is picked up. So this is a good thing, to have highest point of single tooth contact. The other side of that coin is tip loading. So if the contact ratio is too small, like 1, then I have the load applied at the tip of some tooth at some point in the mesh. And because that's further away from the root, I have a bigger moment and thus more stress. Okay? And we'll see this same term show up in a table in a few minutes. This says that you always have dynamic loading no matter how you are applying load to the gears. You could have constant torque, but because the teeth individually are coming in and out of mesh, they only occasionally see a load. And the top sketch shows a repeated loading. That's a term that we met in Chapter 6 when we talked about fatigue loading in general. Same idea, we have a load going from 0 to some peak value, so it has a mean value equal to the alternating component, and that should immediately bring to mind Goodman diagram in order to find the stress state and the safety factor of that particular gear tooth. Now, if I have an idler, you recall an idler is a gear in between 2 others placed there primarily to reverse direction, and since it doesn't affect the ratio of the gear train, it's considered an idler. It's not doing any useful work. It's just turning the output around in the other direction. But it lives a harsh life because it's in contact with 2 teeth, with 2 gears, I should say, one on either side, and thus one of them is pushing it one way and the other is pushing it the other, so it has fully reverse loading, and the peak values are just as big as the repeated load values are up above. So the alternating here is twice as big on the idler as it is on the other guy, and the mean is 0. So I have fully reverse loading on an idler. And we'll take that into account with a factor when we do the calculations. We should expect that the gear teeth will see both bending stresses due to the fact that they're cantilever beams, essentially, with loads transverse to the beam. And they also will see surface stresses because they're rubbing on one another, and we have a Hertzian contact situation such as we discussed in Chapter 7. Now, you I think, understand now that when we have non-surface type loading, non-Hertzian stresses, we can, with the right materials, get infinite life. Steel being a good example, we have an SN diagram, strength versus number of cycles, that eventually flattens out around 10 to the 6 cycles. And if we stay below that number with some safety factor, we should expect it to never break. And that's true. And thus we can expect to be able to design our gear trains so that we will never fail the teeth in essentially infinite time. That's not true of surface failure, because as we learned when we discussed that in Chapter 7, there is no equivalent endurance limit for surface loading. And if you run things together in surface loading long enough, even at relatively low stresses, eventually you'll start to pit the surface. Now, if the stresses are low, it's going to take a long time for that to happen. And so I typically design my gear set to last more cycles than I care about, and knowing that eventually if you run it long enough, it's going to start to pit and I'll wear the gears out. So wear is the ultimate failure method for everything. Everything wears out given enough time. So we just have to accept that, and usually we can make sure they don't break in service, but we can't get infinite life in surface. I've already said that. And if I don't lubricate them well, or if there's dirt in the mesh, then I'm going to have early failure, probably due to one of the other wear modes of adhesion or abrasion. So if I have unhappy gears running in a rock crusher environment or something like that, where the rock particles are getting at the gears, not a very good thing, they're going to wear out, probably pretty quickly. So we'd like to have good lubrication, and I think it's a true statement to say that it's very rare for a gear in an automotive transmission to fail by bending, that is to break a tooth, in service for the life of the automobile. The automobile will be in the junkyard before you ever break a tooth, unless you abuse it. And I have some examples in the closet, which I didn't think to go get at the beginning of class, of such broken teeth, but they were trotted into me by members of the motorsports club who had taken them out of their transmission after they had a drag race or something of that sort. So the overloads did the teeth in, but now we have a situation where the loads were greater than the designers expected them to be, and sure, I could break anything if I put enough load on it, right? Stick a dynamite in, I could break it for sure. But if it's used the way it was intended, you should expect the teeth never to break in an automotive transmission. However, they eventually will pit, but probably not in 200,000 miles, because they're designed to run that long before you run into that problem. Now, this is a very simplistic model of a tooth. There's a cantilever beam. It doesn't show any shape. It really has the involute shape and all that jazz. But as a simplistic model, I have a cantilever beam. I got an end load, which is this WT, the tangential load. It's got some thickness, which is intended to represent the thickness of the root, where it really matters, and a length L, which is the point, the distance out to where my load is acting, which might be the tip of the tooth, or it might be this HPSTC business, where the highest it ever gets to because of the multiple teeth in mesh. Now here's a more realistic looking tooth, although it's a little bit funky, because it looks like I have some interference here. It's getting narrowed down where I'd like it to be at. It's just a schematic, and it points out that we have the narrowest portion here is the weak link. That's where I would expect it to break. I show tip loading up there. And here's an equation which is simply MC over I. It's a beam in bending. So MC over I is the basic equation. But here we've substituted the loading in the nomenclature that's typical for gears. In other words, the load is WT. PD is the diametral pitch. F is the face width, which would be the thickness in and out of the picture here. Clearly, the longer the tooth, the more meat I've got, and thus the longer it will last. And what else we got there? We got this thing called Y. Well, that's a geometric factor, so-called, that was created by a guy named Lewis, I think back in the mid-1800s, I want to say, somewhere that far back in time. And he was the first one to really figure out what the crazy shape of the tooth was doing to the stresses. And so he built that into what became known as the Lewis form factor. And I don't even show you the equation for the Lewis factor in the book because it's obsolete. And it has been replaced by a factor that AGMA calls J. So the J factor is the up-to-date Lewis factor that was originally called Y, and it contains all of the elements of Lewis's geometric form factor, but also includes effects of stress concentration in the fillet at the root of the tooth. And the J factors are determined empirically, and we have to go to a table to get them, as you'll see. So here is the up-to-date formula for bending stress in a gear tooth. This comes from AGMA, which you may recall is American Gear Manufacturing Association. So this is a U.S. standard. If you go to Europe or anywhere else in the world, you're going to find other standards in use for gears. Germany has DIN. Don't ask me what it stands for in German. It's an acronym for something or other. And of course there's ISO as well, which is probably universal across the world. And so, and Britain had its own standard, which I think they've abandoned in favor of ISO, and so forth and so on. And they'll all be a similar looking formula, but there'll be particular differences. And I don't go into any of those in the book other than to give you a few SI versions of some equations, largely involving the module rather than the diametral pitch. So the book is focused on the American standard. We're in America, after all. So up at the top we see, well, here I give you both SI and US versions of the same thing. But the difference is, notice that PD, which is diametral pitch, is in the numerator of the US equation, and M, or module, is in the denominator of the other, because they're reciprocal. But other than that, it's the same equation. So in other words, I'm using AGMA standards to do metric gears with that second equation. I'm going to get all these K factors and whatnot from AGMA. So that collection of K stuff is more or less the same stuff we used in Chapter 6 to reduce the strength of our materials. You know, size effect and all that jazz. They're listed right here in this table, as a matter of fact. Well, let's just go through the table. I've already talked about F is face width, J is the modern version of Y. KV is a dynamic factor which depends on tangential velocity, and there's a figure right out of AGMA's manuals that lets us select that number appropriately. And I'll show you each of these in turn. This is just a preview. Km is the load distribution factor for account for misalignments. So this tries to take into effect the fact that maybe my two gear axes aren't dead parallel and a little bit of error, and so my two gears aren't quite meshing properly and they're pushing more on one side than the other and so forth. Ka is an application factor which tries to take shock into account. I'll show you a table for that. Ks is size factor, which is the same idea as we did in Chapter 6, where we're using data that's based on a 3/10 of an inch diameter test specimen, and we decide that if the R piece is bigger in physical size, there's a greater likelihood of flaws being present in the cross-section, and so we factor down the numbers by some amount to account for that. This is a similar concept. KB is a rim thickness factor, and this is only applicable when I have, instead of a solid gear, I've got a gear with spokes, real big gear, and there's a rim, and I might fail in the rim as opposed to the tooth. So this is going to take into account the fact that I might have a rim failure. KI is the idler factor, and here's where we account for the fact that the idler lives a tough life with this fully reverse loading, and we bump up its load by 1.42, square root of 2, to account for that. And we use 1 for a regular gear, non-idler gear. Here's where I return to the idea, but contact ratio is recommended to be between 1 and 2. And this is the contact ratio, M sub P. Z, I think I showed you a formula for Z in the other lecture. It's a big mess of stuff divided by the base pitch, which gets me a value for MP. And it's based on the assumptions you see here. No interference between, actually the whole bending stress equation is based on this set of assumptions, that we have a contact ratio that's between 1 and 2. So even if I had 3 or 4, I would call it a 2, because to be conservative, because I'm going to assume that I don't have real good contact between all those 3 or 4 teeth. No interference between the tips and the roots. I don't have the teeth digging into one another as they go through the mesh. No pointy teeth. There is backlash, non-zero backlash. That's realistic. There always will be. The root fillets are standard as defined by AGMA, so the dimensions are standardized, and so are the finishes. And that, of course, affects stress concentration greatly, right? So that's essentially an attempt to control stress concentration. And it neglects friction, so it's assuming good lubrication. So if any of those things are not true, then you're going to have to add some more fudging to your numbers to account for that, which is not specified here. This is what I was referring to by not well meshed gears. And this comes right down to how much money do you want to spend. So if I want to spend cheap money for gears, I'll probably get a set that look like this. So this shows 2 actual gears in mesh, and they've got a big contact ratio because they're both very large in diameter compared to the teeth size. And notice that I can see the second pair down. Actually, it's the first pair because the top one isn't a pair. I'm touching definitely there, Next one is flapping in the breeze. Next one's flapping in the breeze. And one up from the bottom is actually touching. So for that whole collection of stuff, I really have two teeth touching one another, because these are not very high quality teeth. Now, AGMA has specified a quality number for gear teeth, which has to do with how careful they're manufactured. And also, as you might expect, affects the price. So the higher the quality number, the more expensive the gear. More care is taken in actually making it. And those quality so-called QV numbers range from somewhere around 2 or 3 up to about 14. And I show you this table. I think it's going to show up on another slide too. And here they recommend, this is AGMA again, recommending, if depending upon your application, they suggest that you need a gear of this level of quality. So at the very bottom, cement mixer drum drive, cheap, crummy gears that they're going to live a hard life anyway, and it's not, you know, it's not an accurate situation. I'm turning the drum so I can mix the cement. No big deal. No great accuracy required. Halfway down, I got a paper making machine that's 6 to 8. Then I got a washing machine at 8 to 10. And mainly, these numbers are going up because you're trying to control the noise. Automotive transmissions 10 to 11 up near the top because you don't want noisy gears in your transmission. And you also don't want to wear out in a hurry. Radar antenna drive, I don't want vibration in that, certainly. Marine propulsion, 10 to 12, they're all the same. Aircraft engine, a little bit better. Gyroscope, 12 to 14. Gyroscope's a very precise device. If I have any bad teeth in that, it's going to vibrate and the gyro won't work, right? So now let's look at each of these factors that we have to worry about in turn. So the so-called dynamic factor, that was the KV, which is in here someplace. There it is. There it is. And they give us a formula for that. It's an empirical formula. Whenever you see something like this with an A and then a B to the B power or something like that, that's been fitted to data. So it's an exponential function fitted to data. So it's A over A plus the square root of VT. Now VT is the velocity, the tangential velocity in the mesh, which is easily calculated. You know how fast your gears are turning. You know what the radius is. V equals R omega from kinematics. And I think, if I remember correctly, the VT has to be in certain units, because any empirical formula will be based on some data that was done in some units. And I think it's feet per minute, but check me on that in the text. I'm not sure I show up on the slide here. Maybe it does. So here, or to go back to the formula, so we have A over A plus square root of VT to the B power. A is defined as 50 plus 56 times 1 minus B. So A is in terms of B. B is 12 minus the quality number, which you pick. How much money do you want to spend? To the 2/3 over 4. So with a choice of QV, in essence, I can determine what this factor is. And this plot shows these empirical curves for various values of QV, with the low numbers being the crude gears, the high numbers being the very good gears. And notice that these are all a function of the pitch line velocity. It is feet per minute, or on this scale it's meters per second. So you have to be careful with your units here, because they did the data in some units or other, and you've got to use the same units, so you'll get a wrong answer. So notice these curves end abruptly, and it's because they didn't test beyond those levels of velocity, which also sends a message that if I have high speed, I want better quality gears, which makes sense, right? So for low speed, I can get away with crummier gears. So I could read this off the chart and get my KV, depending upon which QV I pick and how fast I'm going. So if I have a KV of, KV and CV are the same thing, by the way. So if I have 4,000 feet per minute and I have a quality of 8, then I've got about a 0.62 or something like that. So I could just read it off the chart somewhat crudely, or I could do this calculation that I show up here. And here's recommended gear quality versus pitch line velocity, and that's more or less indicating where these curves stop. So if you're really fast, you want a high quality gear. Here's the same table I had on the other slide, indicating that for certain applications you need better quality gears. All that's pretty commonsensical. It's in the denominator So small number, which these tend to be, see it's all less than 1, is going to drive the stress up, right? So if I have a small quality of a small velocity factor due to the low quality, then I'll have an apparently higher stress to compare to my strength. Here's the geometry factor J. Remember, this grew out of Lewis's form factor, but has more stuff in it. And I give you a sample of tables out of the AGMA manuals, which, by the way, fill a shelf. I mean, the library across the street has them. We subscribe to them. Gear companies pay tens of thousands of dollars a year to get these documents, to be members of AGMA. I get them for the university for $25 a year from AGMA, because we're a university. So they send them to me, they go to the library, and they're there for you to peruse. Actually, they put them all on CD now, so you actually don't have to go to the library. Everything's in PDF form. So at any rate, I've reproduced a few of them in the book to give you an idea. If you see a U, that means undesirable or unspecified or something like that. In other words, there's too few teeth. I have an interference problem. So they don't recommend that you use fewer than 21 teeth for 20-degree full-depth teeth with tip loading. And this chart right below it is for this highest point of STC loading, single tooth contact loading. And numbers are a good bit different, 0.24 against 0.33. And that's in the denominator too, I think, so smaller numbers are going to drive the stress up more. So the tip loading will give you higher stresses than this highest point of contact. So the way you use this chart is you decide what do you have for your number of your gear teeth rather over here, and how many pinion teeth do you have over here, and you have a different factor perhaps for the pinion and the gear. P is pinion, G is gear. So these all look pretty close. This is a little bit difference here, there. Otherwise they're similar. And down here there are a little bit of difference here between pinion and gear. So you actually have to do your calculations separately for the pinion and for the gear. You'll have different stresses in each because of this different factor. It has to do with the fact that the tooth shape is a little bit more aggressive with a small number of teeth on the pinion. Other factors, Ka and Km, we'll take those up here. Km is the load distribution factor. And here you choose your face width in inches and or in millimeters, and you pick a Km off this table. So notice that the bigger the face width, the larger this Km becomes, and Km's in the numerator, so that's going to also drive the stress up. So in essence, you're factoring away some of the advantage of the wide tooth based on the premise that it's so wide that my alignment will be such that I won't really take advantage of all that wideness, and it won't really be touching over the whole width. Application factor Ka takes into account the fact that I sometimes have nice, smooth, quiet machinery. Other times I have noisy, high vibration or shocky machinery. This factor is 1 if I have a driving machine which is uniform, i.e. an electric motor or a turbine, and a driven machine which is also uniform, perhaps a generator. So if I have I don't know why I'd have an electric motor driving a generator. It doesn't make much sense. But I have a turbine driving a generator, then I would have a 1 for this Ka, and it wouldn't increase the stress at all. But if I have that same turbine driving, I don't know, maybe an air compressor or something like that, it might go to 1.25 and so forth. And if I'm in a very heavy shock and driving it with a single cylinder engine, I got 2 1/4. So I more than double the stress then, because this is in the numerator also. So you get the idea? All very empirical. But that's the way gear data has been developed. AGMA has spent literally over a century testing the dickens out of different gear combinations and developing all these data. And they are supported by the gear industry, who pay these thousands of dollars to be members. And then the AGMA shares the info with everybody. So everyone's on the same level playing field to compete on whatever basis they can compete, better price or whatever. And as I mentioned before, anybody's gear will mesh with anybody's gear if they're all made to the same standard. So it's a very, very sensible approach. Okay, so we got another bunch over here, KS, KB, KI. Size factor, KS. Now that's the same as the size factor we had back in Chapter 6, which I mentioned a few minutes ago, where our test specimen's the size of my index finger, and I might have a big part, and so I factor the strength down, or the stress up, which amounts to the same thing. I use them as stress increases in the Chapter 6 as well. But in this case, all the test data that's generating the strength information is with real gears and real teeth. So the sizes are correct. So I don't have to fudge the size because it's the real deal. So we're testing real gears. So we call it 1. So it might as well not even be there. The rim thickness factor, KB, is 1 for a solid gear because there's no rim. And in the text, I give you some clues from AGMA as to what it should be for a gear with a rim. And the idler factor we mentioned earlier is square root of 2 for an idler and 1 for a non-idler. And that accounts for the fact that I have the higher stresses on the idler, which is this picture that you saw earlier. So here's a regular gear, there's an idler. Okay? Are there any questions at this point about bending stresses? So this is the one that they will succumb to eventually. So as I said earlier, we can design them not to fail in bending because we have infinite life possible, but they'll eventually succumb to surface fatigue. Now, there's been a lot of research done in gears over the years, as you might imagine. I mean, it's big business. There's an awful lot of gears used in machinery. And the fact that the U.S. standardized this so many years ago, century ago, has really helped our manufacturing economy, as you might imagine. So it's a very, very sensible approach, rather than having 15 different sizes of gears out there that no one can ever figure out how to put together. So a fellow named Buckingham, who I think was a prof at MIT a long time ago, was the first to develop an equation that was appropriate to calculate the surface stresses in gear teeth, because they have very funny geometry. And his equation has been, again, modified and improved by AGMA over the years. It's still referred to as the Buckingham equation, but its official name is the AGMA pitting resistance formula. But it's based on the Buckingham equation, to which they've added some goodies. So here I'm using sigma sub C as opposed to sigma sub B, which B stands for bending. C, I don't remember why I picked C. Next letter on the alphabet after B, probably. But this stands for surface, in my lexicon at least. And so we have some factor called CP, which is an elastic coefficient that I'll define momentarily, times the square root. And here are the usual suspects. We got WT, which is the tangential load. F is the face width. D is the pitch diameter. And I is the analog of J. It's a different factor, but it's, in quotes, the J for surface conditions as opposed to bending. Okay? Doesn't look anything like J in terms of the mathematics, but it's serving the same purpose. And then we have this bunch of other factors, C. In most cases, in fact, I say it right here, CA, CM, CV, and CS are the same as KA, KM, KV, and KS, which are the letters used for the bending equation. So application factor would be CA. CM is the load distribution factor, I think is the fancy name for it, when your two gears are not exactly parallel to one another. CV is the velocity factor, and so forth. So we'll just look at the ones that are not equivalent to the K's. Let's take CP first. This is called the elastic coefficient, and it accounts for differences in tooth materials. And there's this messy equation to calculate it. And if you look at the equation, you'll see there's only really two things in it. There's the Young's modulus in two flavors, one for the pinion, one for the gear. So this accounts possibly for two different materials between pinion and gear, which is not unusual, or they could both be the same. And V is, of course, Poisson's ratio, and again, we could have a slightly different ratio for pinion and gear if the materials were different. And pi is thrown in there for good measure. And we can calculate this, and all of the tables that AGMA has developed is using an assumed Poisson's ratio of 0.3. And in the literature, you'll see many a reference to the fact that most metals have a Poisson's ratio of about 0.3. And if you look up a particular steel alloy, you might find it's 0.28 or 0.29. So it's true they're all around 0.3. So if you wanted to have a more accurate number, you could look up the particular Poissons for the particular material you have, stick it in the formula, and get that value. But the tabular data associated with this, which we'll see in a moment right here, are all based on Poisson of 0.3. And since we don't have an awful lot of different Young's moduli either, you see a good bit of difference here. Pinion material down the left, gear material across the top, and they're both the same lists. So I could have steel on steel, steel on iron, iron on iron, nodular iron on nodular iron, et cetera, et cetera, et cetera, any combination at all. And the numbers you see in the table body are what would come out of that messy formula involving the Poisson's ratio and the Young's moduli of the two materials, if you did the calculation. As I said, it's very common to have steel on steel. It's also very common to have steel on bronze, either tin bronze or aluminum bronze. Those two run very well together. Quite often you'll have a steel pinion and a bronze gear, because the pinion will have somewhat higher stresses because of the small number of teeth. So I use the stronger material on it usually. Steel against cast iron runs very well. Same deal, steel pinion, cast iron gear. Gray cast iron, which is the cheap stuff, which has lousy tensile strength. And we know this is a tensile stress type failure, this bending, right? So you'll see that the numbers get kind of low for cast iron. Not that much lower, but they are lower. It's only 22 10 to the 6th psi for Young's modulus against 30. But cast iron for a gear and with a steel pinion is a popular combo because the cast iron will tend to run quieter, and that's because it has good internal damping, which is typical of cast materials in general. Because of their granular structure, they tend not to transmit noise and vibration as effectively as a piece of solid steel, which is a really good bell. So if you hit a piece of steel with a hammer, it really rings. You hit a piece of cast iron with a hammer, you get something more akin to a dull thud, because the energy is getting absorbed by all these interfaces between the graphite and the iron that are scattered throughout the microstructure of the material. So, and they run well together, they wear well. So steel against cast iron is a popular arrangement. Likewise, steel against bronze. If you're in a marine environment, you might have bronze on bronze, or you might have stainless steel on bronze, or something like that to counteract the corrosion problem. So again, I can either calculate the CP, or I can go to this table and grab one of these numbers for the particular combos of materials I have. And that brings us to the surface geometry factor I, which is sort of filling in the role of the J for the bending conditions. And a much simpler formula. J's formula is just, I struggle trying to get it formalized. They don't give you a formula for it. I tried to develop one, and I finally gave up after a long struggle. I couldn't get the tables to match, so I just put the tables in. It was my one failure in getting rid of tables. I did it to Peterson. I did it to a whole bunch of other stuff. I managed to get fitted functions that I could grab on the fly. I was never able to do it with the J's, but they can do it with the I's. And here we have radius of curvature is that rho, Greek letter R symbol, and we have the radius of curvature of the pinion and the gear, reciprocated, multiplied by the pitch diameter of the pinion, all divided into the cosine of the pressure angle, to give us a factor I, which we put into the formula in the denominator, so small numbers will give bigger stresses. I've already said some of this. Typical materials, I've already mentioned the first three. Non-metallics are quite popular for gears as well, and I list three of them there: nylon, Delrin, those are trade names, and phenolic, which is a generic name. Phenolic gears go back a long way, all the way to the 1900s. They're one of the first plastics ever developed. They're made of urea formaldehyde, and they're a thermosetting resin, which means they don't melt once you set them initially. And they were always, typically, I shouldn't say always, they were typically made with cloth matrix. So it was an early composite material, actually. It was layers of cloth, not fiberglass cloth, that wasn't invented yet, just cloth, like linen, and impregnated with this phenolic resin, which they then set using heat. They thermoset it so it became hard and rigid. And their main claim to fame is they run really quiet. And for years they were used in the camshaft drives in engines down into the 40s, 1940s. They wore rather badly because it's soft, and eventually you'd wear the teeth away. But in the meantime, you didn't hear much noise because of the plastic running on steel. The mating gear would be steel. The generic name of Delrin is acetal, sometimes pronounced acetal, spelled just like it sounds, A-C-E-T-A-L. There are only 2 companies that make it as far as I know. DuPont makes Delrin, trade name. Celanese makes Celcon, trade name. They are slightly different chemically because of patent issues, but they have very similar properties. They're a very, very good engineering plastic for lots of applications. Quite strong as plastics go, about 10,000 psi tensile strength. Compare that to aluminum, which might be 20. Steel, which is a real cheap steel, is 40, 35, 40. So it's not shabby in terms of strength. Nylon, similar strength, about 10,000 psi ultimate tensile. Both are somewhat slippery, not as slippery as Teflon, but they also make them alloyed with Teflon and also alloyed with molybdenum disulfide, that black slippery powder. So they're very expensive with these alloys because only a couple of companies make them. Rulon is one trade name. I've used them in many applications, and they work quite well. And the big deal with those is you can run them dry with no lubrication, particularly if you've got the molybdenum disulfide and the graphite in there, because that's self-lubricating. So if you have an application where you cannot have oil, and there's lots of those, think medical products, food products, those machines that are making your food for your table and your medicines for your veins or whatever, you don't want any oil in them. So you can't have oil flopping around on the cams and the gears and those things. They got to run dry. Or if you do have oil, you got to seal it up in a box very well. Okay, let's talk about the various strengths of these materials. And again, we have the advantage here of this organization. AGMA has done a huge amount of testing to get fatigue strengths. Now, they're not just doing tensile tests. They're running these things under regular gear loads, so they're fatigue loading them. So they're developing what amount to endurance strengths. So that's a big help to us as designers, because now we don't have to, with gears, do this fudge of saying, well, let's take the ultimate tensile and divide by 2 if it's steel, multiply by 0.4 if it's something else, and then we'll start, factoring in all this other stuff for size and surface and all this jazz. That's unnecessary in large part because here we have tests done on the real deal. Gears made of the right material with the right kind of loading, with fluctuating loads and so forth and so on. And they have these data for both bending and surface fatigue. So this is really useful. So they're partially corrected. Remember in Chapter 6 we started with what we called an uncorrected fatigue strength, which was typically half of the tensile. Because all we have usually is the tensile strength data for a given material. It's very expensive to do fatigue tests because you've got to run them for months to get up to 1 million cycles or whatever. Some other differences here. These strengths are done at 1E7 cycles, 10 million instead of 1 million, or 5E8. 5E8 is typical for aluminums. I'm not quite sure why, because that's a point on a curve that's still going down, so it made sense to go out beyond 10 to the 6th. 1E6 is where the typical knee occurs for steel. These guys go out to 10 to the 7. And also, they're stating them at 99% reliability, whereas our tensile test data for ultimate tensile strength is quite often at 50% reliability. In other words, you're as likely to get a piece from the steel store that's weaker than the stated number as stronger, which is why we then have to bring in the reliability factor if we want to be conservative and pull that down based on whatever reliability we feel comfortable with, 90%, 99%, you name it, right? So already they've done this at 99%. So if you want to be more conservative than that, there's a table of numbers that lets you pull it down for 99.99% if you want. Or if you want to live dangerously, you can go back to 50% and increase the strength. And those numbers are all provided by AGMA. As I said, the test load was the real deal. It's fluctuating, so it's got mean stress built into it. So I actually don't even have to draw the Goodman diagram in this case. I can simply compare my stress to my strength because it's apples and apples. My stress condition is fluctuating, and my test data is fluctuating. So I don't have to do all that extra work of the Goodman diagram. Makes it really easy. Now they've hung their hat, they being AGMA, on the Brinell hardness of the material, which is a very good way to do it. It's a bit crude. If you bothered to read Chapter 2, which I suggested you do as the first reading assignment, which is a review of materials, BS 2001, in that chapter somewhere you'll see a statement that you might not have encountered in ES 2001 that says that a reasonable estimate of tensile strength of a material, particularly metal, and particularly steel, I think it's primarily steel, is to take the Brinell hardness number and multiply by 500. And that gives you the ultimate tensile strength, I think, in kpsi. Check me on that in Chapter 2. I'm not certain of my memory on the units. And the advantage of that is a hardness test is ridiculously easy to do, assuming you have the gizmo to do it. Because all it does is takes a ball of diamond, or in some cases a pyramid. I think Brinell may use a pyramid. Each of the tests, Rockwell, Brinell, Vickers, and there's one other that I can't think of, all have a slightly different shaped indenter. But they all work on the same principle. You have a given load, I think it's 3,000 grams in one of these tests, and you impart that to the surface of your metal piece, and then you get out a microscope and you measure how deep the dent is, or how wide the dent is. And that varies with the particular hardness number. Sometimes they measure the width, sometimes they measure the depth. Each guy wanted to do it a little differently and put his name on it. Mr. Brinell did it one way, Mr. Rockwell did it a different way. So it's really simple. If I have a piece of steel that's in two pieces, it broke out of a machine, and I've been asked to do an analysis of this and redesign it so it doesn't break. And the first thing I say to the guy is, do you know what kind of steel it is? I don't know. Just came out of the machine. No idea. I bought the machine used. Not a clue. So I could take that to a Brinell testing machine. I can do a hardness test in literally 5 minutes, take that number, multiply by 500, and I've got an approximate tensile strength for my material. So very, very handy way to get, it's a rough number. There's a good bit of noise in it, but it's better than nothing. So with that little bit of information and this empirical formula for different grades of material, grade 1, grade 2, those are defined in this AGMA specs, and Brinell hardness on this axis, I can get myself a tensile strength. I'm sorry, a fatigue strength. This is fatigue, not tensile. So this is right to fatigue strength, either in MPa or PSI. And these are published as a table, right in the AGMA specs. And of course, not all materials are represented here, and I don't even have the complete table. So if you went to the actual AGMA standards, you'll find more than I show here. I picked out some representative steels, some cast iron, some nodular iron. Do you all understand the difference between nodular iron and cast iron? Cast iron, also called gray cast iron, is very poor in tension. It's graded as class 20, 30, 40. That's the tensile strength. 20,000, 30,000, 40,000. Nodular iron has a different physical structure, and its strength is up in the 80, 90, 100,000 psi. So huge difference. More expensive, as you might expect. So I can go in here, get some numbers for bending fatigue strength. I see I'm just about out of time, so I'll wrap this up. I've got some factors I got to apply as we did in Chapter 6, not as many as before. Temperature, reliability. Different table, though, because remember 99 is our 1.0 here. And a life factor, which means I'm at 10 to the 7th for the data, which is right here, but if I only want 10 to the 4 cycles, I can be stronger. So this is an SN curve, I can work my way back up the SN curve, and that's data is provided. And we have also curves for fatigue strength in surface fatigue. So everything you need to know about gears really is in this AGMA database. And if you follow their methods, you're going to come up with a gear set that pretty well works. I'll stop there. We'll see you tomorrow, I hope.